Gravitational waves are the curvature of spacetime, generated by accelerated masses, that propagate as waves outward from their source at the speed of light. They were first proposed by Oliver Heaviside in 1893 and then later by Henri Poincaré in 1905 and subsequently predicted in 1916 by Albert Einstein on the basis of his general theory of relativity. Later he refused to accept gravitational waves. Gravitational waves transport energy as gravitational radiation, a form of radiant energy similar to electromagnetic radiation. Newton's law of universal gravitation, part of classical mechanics, does not provide for their existence, since that law is predicated on the assumption that physical interactions propagate instantaneously, at infinite speed, showing one of the ways the methods of classical physics are unable to explain phenomena associated with relativity. The first indirect evidence for the existence of gravitational waves came in 1974 from the observed orbital decay of the Hulse-Taylor binary pulsar, which matched the decay predicted by general relativity as energy is lost to gravitational radiation. In 1993, Russell A. Hulse and Joseph Houghton Taylor Jr. received the Nobel Prize in Physics for this discovery. The first direct observation of gravitational waves was not made until 2015, when a signal generated by the merger of two black holes was received by the LIGO gravitational wave detectors in Livingston, Louisiana, and in Hanford, Washington. The 2017 Nobel Prize in Physics was subsequently awarded to Rainer Weiss, Kip Thorne and Barry Barish for their role in the direct detection of gravitational waves. In gravitational wave astronomy, observations of gravitational waves are used to infer data about the sources of gravitational waves. Sources that can be studied this way include binary star systems composed of white dwarfs, neutron stars, and black holes, events such as supernovae, and the formation of the early universe shortly after the Big Bang. In Einstein's general theory of relativity, gravity is treated as a phenomenon resulting from the curvature of spacetime. This curvature is caused by the presence of mass. Generally, the more mass that is contained within a given volume of space, the greater the curvature of spacetime will be at the boundary of its volume. As objects with mass move around in spacetime, the curvature changes to reflect the change locations of those objects. In certain circumstances, accelerating objects generate changes in this curvature which propagate outwards at the speed of light in a wave-like manner. These propagating phenomena are known as gravitational waves. Gravitational waves. As a gravitational wave, that observer will find spacetime distorted by the effects of strain. Distances between objects increase and decrease rhythmically as the wave passes, at a frequency equal to that of the wave. The magnitude of this effect is inversely proportional to the distance from the source. Spiraling binary neutron stars are predicted to be a powerful source of gravitational waves as they coalesce, due to the very large acceleration of their masses as they orbit close to one another. However, due to the astronomical distances to these sources, the effects when measured on Earth are predicted to be very small, having strains of less than 1 part in 1020. Scientists have demonstrated the existence of these waves with ever more sensitive detectors. The most sensitive detector accomplished the task possessing a sensitivity measurement of about 1 part in 5 times 1022, as of 2012, provided by the LIGO and Virgo observatories. In 2019, the Japanese detector Kager was completed and made its first joint detection with LIGO and Virgo in 2021. A space-based observatory, the Laser Interferometer Space Antenna, is currently under development by ESA. Another European ground-based detector, the Einstein Telescope, is also being developed. Gravitational waves can penetrate regions of space that electromagnetic waves cannot. They allow the observation of the merger of black holes and possibly other exotic objects in the distant universe. Such systems cannot be observed with more traditional means such as optical telescopes or radio telescopes, and so gravitational wave astronomy gives new insights into the working of the universe. In particular, gravitational waves could be of interest to cosmologists as they offer a possible way of observing the very early universe. This is not possible with conventional astronomy, since before recombination the universe was opaque to electromagnetic radiation. Precise measurements of gravitational waves will also allow scientists to test more thoroughly the general theory of relativity. In principle, gravitational waves could exist at any frequency. However, very low frequency waves would be impossible to detect, and there is no credible source for detectable waves of very high frequency as well. Stephen Hawking and Werner Israel list different frequency bands for gravitational waves that could plausibly be detected, ranging from 10⁻⁷ Hz up to 1011 Hz.